I should introduce our first speaker, Dr. Denis Schiozer from the State University of Campinas. He's going to talk about his research work at the university. Thank you.
Thank you, Andrew. Good morning. Welcome to Brazil. Thank you, Energi Simulation, for organizing this summit. It's a pleasure to be here. I'm going to talk about model-based reservoir management in 3 stages: life cycle, short-term, and real-time. The focus of the presentation is the digital twin that we are planning to use in digital fields. The motivation for this work came from the companies here in Brazil where simulation models are often used to life cycle decisions, but not very often used for short-term and real-time applications. And as the Brazilian pre-salt is going to digital field application, intelligent fields, we need, and the life cycle decisions are very complex and very time-consuming, and we need to speed up these decisions and process for reservoir management if you want to apply them for real time. So the objective is to develop methodologies to improve the quality of the short-term production forecast and decisions, and to integrate this with machine learning and applications for digital fields in real time. At the end, we want to contribute for more efficient energy production. So this is a typical closed-loop field management decision development and management that we apply in petroleum fields. That I've been presenting in the previous year here in the summit. Basically, we have this divided in colors. The green color here is dedicated to build good models for us to use in this decision-making process. Of course, these models are not very effective when we build them, so we need to calibrate these models using dynamic data that we get from the reservoir, which is this red part here. And once we have these models, we use them for decision-making process, integrating this for life cycle decisions. And these 3 colors normally are the colors that we use for a normal procedure for selecting production strategy for the fields. But if we want to apply them for short term, we included this top part here, which is in gray and black, which I will explain later. So we are including the short-term production optimization because the life cycle optimization is very complex. It takes a lot of time. So instead of doing this using all this time, we get some approximate solutions for life cycle decisions, and then we intensify the optimization process to decide the variables that we're going to implement in the next cycle of the closed loop. And also, when we want to implement this in the field, we have a lot of operational noise that I will explain here in the presentation. And before we implement that in the field, we account for this operational noise. So the main idea is to divide this process in 3 stages. The first stage is the life cycle decisions, which we can do it in background, so we can optimize all the production in background, trying to find best solutions for the problem. And once we get a good solutions, we go to stage 2, where we intensify the optimization process to decide how we're going to manage the field, how we're going to control the fields in the short term. And of course, if we change any important variables, we can go back and check if this is good for life cycle as well. And once we decide how we're going to operate the field, we go into the 3rd stage, which is the digital twin, where we account not only for the short-term variables, but also for operational noise that we have. And in parallel, also, we are using artificial intelligence to try to improve the quality of the decisions. So in summary, the life cycle optimization, we can do very complex processes, including uncertainty, the risk analysis, probabilistic decisions. We can use high-fidelity simulation models that are very computational intensive. But in parallel, we get some approximate solutions that we can use lower fidelity processes or lower fidelity models. And these solutions will be implemented as set points for the short-term decisions, that we call here the closed-loop cycle optimization, because we're going to intensify the optimization only for the variables that we are going to implement in the next period. And in parallel, we keep running all the other optimizations to find better solutions. So the second stage, we go very deep into the variables that we are going to implement in the fields. And this, even for these decisions, we are testing to use deterministic model, not only probabilistic, because the uncertainties are not so important for the short term. And of course, we keep checking if these solutions are good for long term as well. And once we decide how we're going to manage the field, how the controls will be operated, we then account for operational problems, operational noise that we are calling here, and then we put this all together in this digital twin model. So the first phase of the research was to test, is a reservoir simulation a digital twin? The answer is yes and no. Yes for life cycle, because for life cycle, these models are already tested. We are using them for a long time to forecast production, to decide how you're going to manage the field for a long time. But this was a not very good model for short term. We had a lot of problems to implement our current knowledge of reservoir simulation to take short-term decisions. We had several things to correct, especially the integration of production facilities and also the correction of the productivity and injectivity that we have in our current models. And definitely it was not good for real time, because for real time we have a lot of operational noise, and also we have a lot of things that happen that we have to be corrected. So the second phase of the research was, can we use data-driven approaches, machine learning, to improve the quality of these decisions? For forecast, yes, we were successful. We could use machine learning to improve the quality and correct the reservoir simulations for short term, but only when we have sufficient data to train the digital twins. Otherwise, if the conditions are different in the future that happened in the past, they are not so good and they need improvements, especially when we have what we call prescribed operations and operational noise. So for taking decisions using these digital twins, we cannot use only machine learning and data-driven approach. We have to combine both. So our current phase of the research is to put all these ideas together in a digital twin reservoir simulation model, where we are using reservoir simulation, high-fidelity, high-flash simulation models together with data-driven and artificial intelligence, where the life cycle decisions and controls are based on high-fidelity simulation models. These are set points for short-term production optimization based on improved reservoir simulation models, and then real-time accounts for operational noise. I'm going to show some examples here. So the general detail methodology was, first, we improved the quality of the simulation models in order to, we use high-fidelity life cycle models to get what we call target approximate solutions, how we're going to manage the field until the end of the reservoir's life. We use this solution to improve the quality of the solution for short term. And in order to do that, the most important thing that we felt was to improve the history matching process or the data simulation process, because our current methodology doesn't calculate very well the productivity and injectivity of the wells. Also, we had some methodology to select the best models to represent the short-term behavior, and sometimes they are not the same as the long-time behaviors. Another thing that's very important is that we have to improve the estimation of the boundary conditions we're going to use for the short term. For long term, this is not so important, but for short term, this is very important, which boundary condition are going to use. So for that, it's very important to integrate with production facilities. We then use what we call human intervention-free boundary conditions, which are the controls without any change. We input in that the prescribed operations every time we have change in the cycles of the WAG, for example, or any other operations that we know they are going to happen. And after all that, we put all the operational noise and react to this operational noise. In terms of data-driven, we had published a lot of methodologies to do this forecast, short-term forecast. But even with all this, if we don't have enough data to foresee all the operations that are going to happen in the short term, we have to filter the results, and we filter considering all the boundary conditions, the restrictions, the prescribed operations. So at the end, we conclude that we have to use hybrid approaches using the reservoir simulation models together with data-driven and considering all these filters. Once we have a good forecast for short term, then we go to optimization, which is the second stage, the short-term controls. Then we check if these controls are good for life cycle. Once we decide how to manage the field, we go to the third stage if we have operational noise. So we put all this together in a digital twin. So just to give an example, what I'm considering operational noise, the failure can be a failure, for example, an interruption in availability of an asset. For example, if you have a problem in equipment and the well have to shut in, or even an unexpected rate of variation, deviation, or disturbance that we have in the operations. For example, unexpected water breakthrough and any other event that happens that we have to correct immediately. So all these events impact the production, injection, and the reservoir dynamics. So we can do manual responses to that, but normally they are slow and inefficient, so we need to do it fast to have using some predefined rules. The examples we are testing so far are in the benchmarks we have in the group. This one is one UNICAMP for 2026, which is a benchmark based on the pre-salt fields in Brazil. We published in 2023 an optimization of this field. It took us 6 months to do it. Of course, we cannot wait 6 months to do a short-term correction and real-time application. So we did a lot of modifications to improve to speed up the solutions for life cycle. For example, we can use less representative models. We can use less time, less iteration in the optimization, simplify the optimization process, and so on. And doing all that, we can perform the optimization that is not perfect, but is good and gets us a good solution in a matter of days. And using this solution, I can apply for short term, which in this case is from 6 months to 1 year, which is the size of the closed loop. And then we can correct every day using a real-time application in the daily application for the next 30 days. Of course, in order to do that, we have to follow our methodology, which is a 12 steps closed loop methodology. We have to build the models in the green part. We have to calibrate the model using data simulation process, including the modifications we propose to account for short-term effects. Then we go into the blue part here, which is divided in several steps that we will not give details today. But at the end of this, we have a good solutions for some representative models of the reservoir. And I'm going to show just an application of the 3-stage optimization. Here's an example. We optimize the fields for life cycle, which is the red one. And after we do that, we intensify the optimization, including the controls for the short term, and we can improve all the simulation models. We check if these modifications are good for long term in the right figure there. And once we get the solution that is good for all the representative models, we can apply this in the real field before we go in the application. I'm just showing here the risk curve considering the base case, then the optimization for life cycle, and then the optimization for the closed loop. Once we propose a solution that is good, in this case, we show that is good not only for short term, but also for the long term, and not only for the representative models, but for the full ensemble. We are confident that this is a good solution, then we apply this in real time. And this is an example of the field operations and operational noise that can happen. We can have operational noise every time we have an operational problem or in a prescribed boundary conditions. For example, if you close a well for maintenance, or even if you have a new well coming in the pre-salt, we have the second wave wells. Anytime we have a modification like this, we have to account for these modifications because the rates will change, and then we have to have a fast intervention on that. And the first step to do this intervention is to check if the well is operating in the full potential or if it's restricted. Then we implement the prescribed boundary conditions and then optimize for real time. Here's an example of a graphic interface that we are implementing. We are going to check checking all the wells, producers and injectors all the time, checking if they are inside the tolerance range, how much they change from the models. Anytime you have a failure or a problem, we're going to have to act in the optimization. We can see, for example, the history data and compare this with the forecast. And anytime you have a deviation from what we're expecting from the models, we can act. Here's an example. We have the 6 producers of the field. In red, we have the production. In green, we have the prediction of the simulation model. And in this particular case, the P16 is having an operational problem, as you can see in the right bottom graph there. So as soon as we have this, we change the controls, so the rates of the P16s change. We have to do a very fast optimization considering all the other wells that are operating, and we get the best solution very fast. And of course, we are investigating other ways to do it. We can do this optimization based on this best simulation model, which is very fast, but we can also use machine learning. We can use surrogate models that have a relationship between producers and producer injectors, or even between injectors, because, for example, in the pre-salt, we have to inject all the gas that we are producing. If you have a problem in an injector, you have to decrease production, and which one's the best candidate to reduce, and so on. So we can decide all this in a digital twin. So in order to do that, we have a fast intervention, and we optimize for an objective function that can be NPV or oil production, or even a multi-fidelity, multi-objective like carbon intensity and so on. So at the end, we have to do a lot of improvements in our current 12 steps methodology that we presented in the last years, with a lot of adaptations and applications for the pre-salt fields that we have in Brazil. We have to modify how we build the models, especially to considering multi-fidelity models. We are using different fidelity models for life cycle and for short term. We had to do a lot of modifications in the data simulation process that we are used to work in the long term for reservoir simulation, especially to account for the transitions between the past and the future, which is mainly caused by the problems that we have in the productivity and injectivity of the wells. Also, we have developed a new way to do a data simulation in the model of the production facilities, because this is also a model and have errors that have to be accounted for. But of course, most of the modifications we are doing are in the decision-making process, especially in dividing this in 3 steps in order to be fast to react to problems that we observed in the field. So we divide this in the life cycle, short-term, and real-time controls. So the methodology is being tested over our benchmark models, and after we finish all this research, we are putting a conceptual digital twin based on reservoir simulation and artificial intelligence. So at the end, what we are trying to do is to do contributions for a better use of reservoir models, including short-term management, better field management, including fast reaction to operational problems, and to put all together in the digital fields integrated with machine learning, trying to build a digital twin reservoir model and contribute to more efficient energy production. And with that, I would like to acknowledge all the members of UNICAMP group, which is the research group that developed all these ideas, university, the sponsors, and the support of software. Thank you very much. I'd be glad to answer any questions if you have it.
Thank you, Dr. Schiozer. We have 2 microphones. Any questions, please raise your hand. State your name and affiliation. And I know this guy, Dr. Haji Beji.
Thank you very much. You presented it for oil and gas energy, and so next year in Netherlands we are starting to inject CO2 offshore Port Rotterdam, and then we get data from the field. Would the change of the physics of CO2 in the subsurface and here oil and gas would make any difference in the algorithm that you are presenting here?
I don't think so. I think the methodology can be applied to all these types of problems. Of course, each problem has particularities. The main thing that we are trying to develop is to check if we need special special type of decisions for each type of problem. For example, in this case of Anything 4 is a typical benchmark case. So we are predefining all the conditions that we can observe in this type of field in order to have very fast decisions. And of course, for other problems, you can do the same. You first go to a simulator, you study all the conditions, you predefine all the things that can happen, the problems, operational problems, and you put all that in a data bank, and then you can apply to other types of problems as well.
That's a very strong point of this framework, which is generic. So that's good.
Okay.
Thanks, Denis. My question is more on the actual implementation of the whole process. There's reservoir engineers, production engineers, management. How do you see this all working together as a whole unit here?
Yeah, that's very important, especially the integration between geologists, reservoir engineers, and production engineers. They have to work together on that because the three parts are very important. If you don't have good models, there's no sense in using this model to take decisions. And if you don't have a good integration between reservoir and production engineers, you are setting wrong boundary conditions. For long-time effects, these are not so important because the rates accommodate over the long time. But for short-term effects, if you have the boundary conditions wrong, you can have 50% wrong rates and so on. So the management makes no sense in doing it. It's better to use your intuition than doing that. So these are very important to be integrated, especially to set the right boundary conditions for the future. And also, as we know that all the models are not have problems, we have to use this artificial intelligence to correct and to set this tolerance range that are possible to change from one time step to another and so on. That's why you are building all this thing together using data-driven and model-based techniques.
Hello, I'm Leo from Repsol Samopac. I just want to complement the question before, the first question that you had. We are doing with your professor in Cepetro, Alessandra Davolio, tool to do synthetic seismic using a field like Sleipner to do and calibrate the simulation. So that's very important also that we can calibrate the Sleipner using as benchmark to see if the simulation is corresponding to the seismic data. So that's very important. We are doing, there is nothing very different to do by characterizing the fields for oil. So we have to do also for CO2 injection. And then after we have to monitor if there are many changes. And a very new paper is going this week for the magazine. So doing Sleipner as a benchmark for CO2 and trying to use all the methodologies that we use in oil and gas. So that's not very different. As Denis said, we have many particularities, but the gross part is the same, so it's very good. So thank you, Denis.
Yeah, this is very important because the monitoring part is very, very important for this process, and the seismic 4D that's being planned to be more often an acquisition in the pre-salt has to be also put together in this thing. And this software that does automatic change from the seismic 4D for the engineers understand the other variables is very important, so we can monitor and react very fast to this type of process as well. Yeah.
Professor Denis, I have one question. Linda,
Oh, sure. Sorry.
thanks for your presentation. What is the perspective for apply the methodology in the real fields?
We are implementing our benchmarks, which are, the complexity is the same, but of course we don't have the operational problems. We have to make the operational problems. So once we have the digital twin ready, we are ready to test in digital fields and see. Our initial idea is to give to reservoir engineers just hints of what he can do. For example, in this case, when the P16 stops, what should I do? I should increase the rate of other wells, which is the best candidate, and so on. We can give some perspectives to the engineers to do it, or we can do, in the future, maybe automatic corrections in the valves, in the actuators that we call, in the ICVs or in the chokes and so on. We can act directly in those. But that's our object. So I don't know if the companies will implement that. Yeah.
Thank you.
Thank you, Professor Denis, for the talk. Any plan to couple with a well-bore model in order to model near well effects such as scale, hydrates, fines migration?
Yeah, that will be our next goal, because as I told, the most important part here for the short term is to have the right boundary condition. If you don't account for this well-bore model, any problem that can happen in the well-bore, then we are going to have a wrong prediction. So we have to incorporate with that. So far, we're integrating with production facilities, but just accounting for pressure drops and restrictions. But in the future, we want to incorporate all the other problems that we know that can happen in the well production. Yeah.
Thank you. Vinicius from Petrobras, reservoir engineer. Regarding to the integration between production and reservoir, we are having a very good experience with CoFlow from CMG. And I don't know if you have in mind using the integration provided by CMG, or you have an in-house software.
Yes, we are testing CoFlow as well. We are also testing Marlin from Petrobras together with our internal software that we have. But in any case, we have shown that it's very important to integrate with these production facilities to get the boundary conditions. Of course, even the CoFlow or the Marlin or the others are also models. They also have problems they have to be calibrated. So we also develop a way to calibrate, based on past data, how to calibrate this model to predict a little bit better the pressure drop in the production system and to get the boundary conditions. So it's important to history match not only the reservoir, but also the production. But we can use CoFlow and any other software that can help us on that. Yeah.
Thank you.
Dennis, let me ask a question on behalf of Mohammed Nidpour online. Is it not better to have the reservoir simulation model as the initial digital twin and train a proxy model on this digital twin to later on make fast real-time decisions and maybe correct the model using reinforced learning when new data become available?
Yeah, that was our initial thought. That's what we are trying to do in the beginning, but that was not enough. Because the reservoir simulation models have a good behavior for long term, but for short term, we need to do all these corrections that I was mentioned. So it's possible, but we can do better than that. We can try to do a little bit better, which is to use artificial intelligence, data-driven, and all the other things to correct. But the most important thing is that if you don't account for this, what we call prescribed operations, that I took as a suggestion of one of the meetings 2 years ago in the summits, 2023, this name, because it's what, of course, even the data-driven or the simulation, if you don't impose what the human will do with the valves and the chokes, we cannot get the right one. So it's very important to account for that. So you can use reservoir simulation or improve the reservoir simulation or proxies, but we have to impose these conditions in the future.
I agree. I mean, the key word is short term. I mean, you can run a model for long term, but life cycle, but then the short term is extremely difficult to kind of do that operational optimization. Mm-hmm. My question myself for you is the digital twin is a deterministic model. So how can you ensure that it is truly representative?
Yeah, we are testing that as well. In the beginning, we are planning to use the representative models, including all the uncertainties. But what we observed is that for long term, the representative models have a different behavior because the uncertainties play an important role for the long time. But for short term, especially for real time, the models are very similar to each other. So there's no sense in using 9, 10 models, even full ensemble, to do the same thing. So if we get the best model based on the past performance, we can do a better short-term prediction. Better than using a lot of uncertainties that they have more or less the same behavior in very short term. Yeah.
Okay, so time's up. Thank you very much, Dr. Schiozer.